So this segment, let's go ahead and talk about salts. So basically this is going to come up when you're thinking about acid-base reactions. So remember that the most basic thought about an acid-base reaction is that the driving force for it is the production of water. So here, just very simply, I've written out that when you have an acid and a base, what you get is a salt and water. So a salt meaning an ionic species, so something similar to table salt, with which you're very familiar, which is sodium chloride, which when you put into a solution, an aqueous solution, you get sodium ions and chloride ions. So an acid and a base forming salt and water is what's called a neutralization reaction. So depending on the solubility of the salt, it may either remain in its ionic form, so in plus or cations or minus or anions, or precipitate out of solution. So you can also have the reverse of this reaction occurring, so where the salt and the water go backwards to form back the acid and the base. And so we call that a hydrolysis reaction. Hydro meaning water. So let's do 4 different scenarios of the types of reactions that you normally encounter. And so the first one, just kind of the easiest one, is the reaction of a strong acid and a strong base. So remember that strong acids and strong bases are strong electrolytes. And when something is an electrolyte, it means that when you put it in an aqueous solution, it completely ionizes to make its cationic states and its anionic states. Okay, so you don't have any of the actual acid or base left lying around. They're both completely dissociated. So here, strong acid, HCl, aqueous, sodium hydroxide, our strong base, aqueous, will go to form the salt, sodium chloride, and water. And so basically, too, something to think about, like going back in your mind, is when you learned things about other chemical reactions. This is kind of an acid-base displacement reaction. So here, because you have a strong acid and a strong base, it's going to be completely neutral, so it'll have a pH of 7. And then again, your products will be salt and water. So let's do another scenario where you can have a strong acid and a weak base. So here, the strong acid I'll use again, one of the most common, hydrochloric acid, HCl, and a common weak base, ammonia. So I've put the unpaired electrons here on top of ammonia because that just reminds you that it's acting as a weak base, which means that it can remove the proton from HCl to make the ammonium. Basically, it makes ammonium chloride, so NH4Cl. Here I've written it in its ionic species just to kind of jog our memories that NH4 is a plus and Cl is a minus. Okay, so you can also, this will go further because remember the strong acid is going to completely dissociate, but the weak base means that we'll have some of this ammonia lying around, NH3, and some of this NH4Cl lying around. So then this ammonium ion can react with water to then recreate the weak base ammonia. And so since the strong acid is here, it's going to dominate, so your pH is going to be less than 7. So since you have a strong acid, your solution will still be fairly acidic. Okay? So then let's do a weak acid and a strong base. So the opposite basically of the previous scenario. So here we have hydrochloric acid as our weak acid and sodium hydroxide as our strong base to form sodium hypochlorite and water. So remember again, water being formed because it's an acid-base reaction. Okay, so since we have the strong base here, that means our pH is going to be greater than 7. Greater than 7. So upwards of 14, right? Because it's basic. And since we have a strong base, that means that our pH is going to remain higher. And so here, similar to the previous situation, when you have the strong base, that means the strong base is going to completely dissociate into its ionic species. But with the weak acid, you're still going to have some of the acidic species kind of lying around. So that means that here, your sodium hypochlorite can react with water to reform your weak acid, your hydrochloric acid. Okay, and then the last scenario is when you have a weak acid and a weak base. And so in this case, I have again hypochlorous acid plus ammonia. I showed the lone unpaired electrons here to remind us that it's acting as a weak base. And so this can remove the proton from the hydrochloric acid to form this ammonium chlorite product. And I didn't write it in its ionic species, but this would be NH4 plus 1 and ClO minus 1. So here the pH situation is going to be a little bit different. So since you have both a weak acid and a weak base, the pH of your overall solution is going to depend on the relative strengths of your reactants. Okay, so then that brings in this concept of something called Ka, which is the acid dissociation constant. So the higher the Ka, the likelier it is that one of these guys is going to give away its proton. So for this particular scenario, it would end up being basic because the Ka of the ammonia is higher than that of the hypochlorous acid. Okay, so you would need to have an idea about what the Kas were for each of your reactants in order to know what the overall pH of this situation would turn out to be. And that is salts in a nutshell.